fino a 4,5.
On utilization of premiumizzato structure pagare please.
No, perché mica del 5 dell'ordine domini di coerenza. Ma anche il pallaggio ma è solamente un canale di passaggio. Certo, quando secondo me tu vai vicino.
Thank you, Mr. Chairman, ladies and gentlemen. May I introduce my co-researcher, Professor Chan,
Questo chi è?
and I cannot explain where of our research contents only on 30 minutes in detail. I have to speak rapidly, so I ask you, listening, be careful. If you take interest in my presentation, please refer to our report, which is just today, 12th, published proceeding the Japan Academy. This content 2 months ago was explained at annual meeting of Japan Academy, 3 weeks after Kobe aspect. From now, I start report. Mr. Chairman, may I ask, I have 30 minutes from now. Yes. Okay. We developed the escasol with paradigm black and produce tremendous energy in this castle. I would like to explain this event. The first subject is deuterium movement from A side with the asterisk A equals 100% concentration, to B side, dB asterisk equals 0, which is separated by C space. Small A case is vacuum condition. B case is deuterium gas with a pressure PD2. C case is solid. D is powder. Here, there is question: what is the most appropriate way to get dB star equal 1 for these cases? How do you think to answer for this question? I believe this crucial situation for cold fusion. As my answer for this question, in A case is impossible as you see, B case is almost impossible. Namely, initial condition of B is same as A. And the pressure BD2 increases with time according by Gilbert's law as figure 2. And as far as experiments in Gilbert territory, it is almost impossible to realize this question. Accordingly, it should need a breakthrough to get out of the Gilbert law. In D case, this is okay. Namely, there is pumping up action in function of paradigm powder, as indicated note B in figure 1. For example, even if concentration A0 on the inner wall surface of the DS cathode is extremely low, paradigm black continually absorb deuterium to achieve the asterisk equal 1 on the wall particle surface. This is spillover effect. And this phenomenon corresponds to incubation period as next described. Next, please. We have ever pointed out the importance of micro defect to the cold fusion. Looking from the bulk material, surface is considered to be a kind of the defect. Therefore, it is expected to increase the effect of the surface micro defects within increasing surface area of relative surface asterisk equal surface area per volume. One extreme state to realize this idea would be powders, which cause spillover effect. This effect causes the powders to function the pumping up action, and the powders continuously absorb deuterium up to the asterisk equal 1, especially in the cluster which with below 10 nanometer in diameter. This star equal 1 should instantaneously be achieved. Such surface effect inherent to the powders enables the homogeneous and highly concentrated deuterization and the feasibility of large cathode. Thereafter, significant effects are not expected in the ordinary surface on the plate and overload with small S star due to the less chemical reactivity. This shows a characteristic of this cathode without powder. This shows a characteristic of this cathode without powder. This experiment also means a test on the role as mentioned in figure 1. The upper side shows some relation between inner deuterium pressure PD2 incubation period tau, which corresponds to critical time of deuterium for outside cathode and current density. We found apparent difference with and without powder, namely between A20 and B0B300. The lower side shows a relation between riser plate of pressure dotted PD2 and current density that was obtained from the upper data. This is very important properties of DS cathode. When the cathode is very large, as our cathode, a large quantity of extra oxygen from anode is produced during deuterium is absorbed in the cathode. Extra oxygen is very dangerous because it becomes very high pressure in our large cathode in the closed cell. Though it is not so afraid in so small cathode used, passed through a small hole to outside, even if, and should be passed through a small hole to outside, even if excess energy is to be lost. Next. This shows the measurement system for the cell power, marked by Q double circle in our closed cell system. And cell power is defined as output minus input. Input and output are shown in right side, and excess heat and cell loss in the left side, respectively. When both excess heat and cell loss are zero or same, cell power becomes zero. In case of no excess heat, cell power is negative and becomes positive when excess heat only overcomes against cell loss. Please take notice of cell power marked by Q double circle as the most important parameter. Next. This shows the excess heat characteristic in DS cathode for long period over 2 years. The A series shows one example of the 1992-93 experiments. The B series shows a retesting results for experiments conducted 1 year later in 1994 using the same DS cathode employed for the A series. Here is the result obtained using standard joule heat source of joule heating by standard resistors in our same cell. Since a new intermittent test conducted over a period of 1,000 hours yielded similar result each time, it was decided to leave the DS cathode idle for 1 year to investigate any change due to aging. In the 3,000 continuous experiments using DS cathode with palladium black 0.1 mole and excess energy higher than 200 megajoule was obtained with an average rate of 50 to 100 kilojoule per hour. It is well known that chemical reaction energy between and deuterium is almost 40 kilojoule per mole, and in this case only 4 kilojoule, which was confirmed by experiment result of figure 2. This test data shows that there is significant difference between the characteristics of the chemical reaction energy and excess energy of the DS cathode. And it is obvious that these energies were produced by fundamentally different mechanisms respectively. These are the newest data repeatedly demonstrate the continuous generation of excess heat long period about 5 months from November 1994 to now. Upper side shows average excess heat is over 10 watts using palladium black. As you see, the strong burst is over 20 watts. Lower side shows the case of only 3 gram per palladium black. Though this is similar to upper side, there is also the strong burst over 15 watts. It is considered that strong burst only generates by earthquakes caused under the special suitable conditions. In here, please take notice of a surprising new phenomenon. Even the long period elapsed 3,000 hours, the new excess heat still more rise up over 50 watt. 15 watt. Since this excess energy is obviously larger than 100 megajoule in all cases, no reaction except nuclear fusion exists in the DS cathode, as you can understand. Therefore, it should be proposed a new model that enables the generation of the continuous powerful cold fusion, namely CPCF. Theory for cold fusion is required to describe the continuous heat generation of more than 100 megajoule per cubic centimeter for a long period of time. For describing the phenomena involved in the cold fusion in the periodic and static field, which takes into account one should not apply the wave mechanics based on wave functions, thermal energy only alone as a cause of perturbation. Instead of this, it should be considered a new type of dynamic wave function, wave mechanics, with inclusion of dynamically fluctuating field. Early in the morning of January 17th, I personally experienced the terrible COVID earthquake in my house, located exactly on the active faulting. However, there were loss damaged areas in a distance of only several hundred meters away from my house. This means that looking from the side of Earth, an earthquake doesn't totally change the surface of Earth, but is a local phenomenon. Cold fusion can be similarly considered to be a kind of the local intense quake of around 10,000 large atoms confined in the equivalent Earth of crystal lattice, which is driven by active holding energy of seismic atom. As a result of this quake motion, it is considered that neighbors of deuterium atoms confined in the lattice field are excited highly energetic, and hence the several chains with this reaction among around 10,000 deuterons is induced. In other words, lattice quake takes place in the crystal lattice, like an earthquake in the Earth, which brings a cold fusion. When you guess that the size of Earth is that of beautiful pearl, the area of Kobe earthquake is equivalent to the size of that quake zone. This means that lattice quake zone is comparable to the size of a cluster, because the lifetime of a lattice quake is in the order of several picoseconds. Lattice atoms surrounding the location of quake are not so much affected. Therefore, it is required to induce lattice quake of about 10 to 12 times per second in order to sustain the continuous emission of excess heat over 10 watts per cubic centimeter. This can be realized by the certain chain reactions to be mentioned later. Thus, results of our experiment was in beautiful agreement with the value that had been obtained by lattice quake model. Next, I would like to explain the lattice quake in detail. This figure illustrates the historically famous radiation damage and molecular dynamics. In cold fusion, such damage itself is not so important at all, but the violent quake of lattice atom, which is induced in the course of damage generation, plays the most crucial role. The lower part of the figure shows the pattern lattice quake, which is obtained from simplest molecular dynamics. The figure shows the violent oscillation of lattice atom when the seismic atom, that is the S atom of 40 electron volt, is ejected to the direction 15 degrees deviated from the 110 direction in the 100 plane. As seen in this figure, it is understood that the directions of 100 and 110 are most important. In this calculation, the Wigner energy, namely the energy of oocyte crash, has been assumed to be 20 electron volt. But this energy changes slightly in between 20 to 30 electron volt, depending on the direction. However, the high energy S atom has generally the energy of 60 to 80 electron volt. Based on this linear figure, we have estimated the behavior of lattice quake by placing deuterium at oocyte. red atom in this figure oscillate very violently, while the pink atom oscillate moderate. On the other hand, the white atom hardly oscillates. When the S atom with 1 megavolt is ejected instead of this 40 electron volt S atom, the deuterium in the vicinity of red atoms generates a kinetic energy of several hundred million degrees, and the pink atoms can give the energy of about a million centigrade degree. Please. Next. This figure shows the giant cascade reaction induced by the 200 kilo electron volt S atom, estimated by VCA method. It is also shown the relation between the same number of vacancies and interstitials. The large quake occurs in the whole area of this cascade, and this zone almost vanishes within several picoseconds and remains the damage of only around 10% in the lattice, and the zone recovers to original lattice. In this very short period, the deuteriums obtain the very high kinetic energy from several million to 100 million centigrade degree. Please. See in the upper part of this figure, the most effective attack directions are shown to deuterium existing all sides. There are three kinds of directions. One is 100, and others are 110 directions. We note that almost converge into such three kinds of directions, irrespective of arbitrary direction of the first attack of S atom. In the lower part, we show the characteristic of three kinds of basic atom displacement of the scape. A in the figure corresponds to channeling tide. This will occur when the O side is attacked by the S atom in 100 direction, where the S atom will have two functions against the deuteriums. One is that this atom repels out to deuterium with high energy at the same speed by crushing the all side included deuterium. The other is that the S atom brings out a channeled big lattice hole. As we can see here, as a red colored zone. Here many deuterium atoms are trapped around it. This hole is shrink in picosecond time scale and induces a lattice implosion, which implodes to high dense energy cluster of deuteriums over around 10 times more than solid lattice density, similar to laser implosion in hot fusion. B corresponds to dumbbell type. This is obtained when O side is attacked by S atom in 110 direction. The S atom again induces the lattice hole by repelling out high energy deuterium from the O side. This is similar to the channel type. C is Clavion type, which appears when lattice atoms in 110 direction and are attacked by the S atom. In this case, the O side is deformed to T side throughout combined OT side with the movement of series of lattice atoms. After that, it again reconstructed as oocyte through the reverse process. As a result, deuterium atoms and electrons are shaped drastically and move at a similar speed with the S atom. Consequently, high energy deuterium atoms collide each other and the reaction occurs. Next, please. I will explain the characteristics of lattice quake. When the S atom induces the lattice quake, two phenomena take place. One is that oocyte where deuterium atom existed is crushed and gives the same velocity of S atom to deuterium as the lattice accelerator. Consequently, if the energy of S atom is assumed 1 megavolt, the deuterium atoms attain the energy of 20 kilo electron volt. The second feature is that the lattice hole of more than around 10 times of more normal oocyte is home, and the many deuteriums are absorbed in this hole, and the hole shrinks very rapidly when the picosecond and lattice quake phenomena is extremely similar to the laser implosion by a gigantic laser beam in hot fusion. Namely, the cold fusion is generated as a mechanism of lattice implosion. Thus, high energy reaction products by this reaction a new generated S atom, and it forms a closed loop, namely chain reaction takes place. As a lifetime of lattice quake is only the picosecond, the lattice quake occurs at least 10 to 12 power second times to maintain the chain reaction. And thus the reaction takes place 10 to 13 powers to 10 to 14 powers times per second. This value is well correspond to our experimental value of continuous heat generation of 10 to 100 watt per cc. The generation of such excess heat continues more than 3,000 hours, and this value corresponds to that 100 to 1,000 of total deuterium vanish from the total number of 10 to 23 atoms per 1 cubic centimeter. This figure illustrates the basic difference between the hot fusion and the cold fusion. For example, the confinement force of deuterium is a magnetic field in the former phase, while it is the lattice field in the latter. Also, in the hot fusion, the plasma is high temperature and magnetized one, but it is the low temperature and high density solid state plasma in the cold fusion. In the hot fusion, the free electrons determines the characteristic plasma property of plasma oscillation and the loss due to bremsstrahlung and the increase in energy of deuterium ions play the crucial role to maintain the chain reaction in hot fusion. In cold fusion, on the other hand, the behavior of lattice atoms plays a fundamental role to increase the energy of deuteriums. The most important condition in this case is a 100% or more increases in concentration of deuterium to generate the chain reaction. Consequently, whichever cold fusion and hot fusion should be needed high energy deuteriums to achieve the reactions. As you can understand, I believe that hot fusion and cold fusion have stood on same line. This figure shows the necessary conditions in hot fusion. The reaction energy epsilon cc must necessarily exceed the Bremsstrahlung energy epsilon b. While in cold fusion, epsilon b is almost zero, and therefore there is no restriction of the above condition. Crucial condition for laser implosion in hot fusion absolutely needs gigantic laser beams and new vacuum spaces for repeated reactions. In cold fusion, on the other hand, is no restriction of the above condition. Only these two materials are included in the DS cathode, and three category of reaction are possible. We can conclude that the excess heat of 200 megajoule per 1 mole can only obtained by the reaction itself. In the DS cathode, pure palladium powder, pure deuterium only. So, no reaction between powders, one side, and the chemical reaction between palladium and the only hot fusion or per 1.1 mole, 0.1 mole. So, 200 megajoule per 0.1 mole, so it should be a active reaction. Thank you.
The slide that had your newest results, the one with the latest data, the plot, do you have that there? The question, it looked to me like you were running for about 2,000 hours, somewhere between 4 watts and the total energy from 500 hours to 2,500 hours. How much energy does that represent?
This total energy, this is over 100 megajoules.
So it's 100. That's 100 megajoules.
Yes.
Thank you.
And this is a very important, I believe, very important phenomenon. Now, continuous now. So I don't know. Until when stop.
And that's sort of, that's sort of
important.
that's like 5 watts out of your system all the time.
5 watts?
It's about 5 watts.
5 to 10.
The output power, 5 to 10.
5 to 10.
5 watts. Yeah. preguntare sulla base.
Other questions? No, thank you again. The next speaker, in place of Dr. Kucherov, we have Professor Sapojin, which will speak on one of energy generation mechanism in unitary quantum theory. Thank you.
Ladies and gentlemen, on one of energy generation mechanism in unitary quantum theory, it is now a well-established fact that in cold nuclear fusion only a small portion of heat results from nuclear reaction, the rest being of mysterious region. In this connection, Professor Peter Hagelstein writes in Cold Fusion, some say that this heat can be explained easily by elementary chemical reaction, phase change, or battery-like storage effects. I have trouble with this explanation. For instance, nickel electrolysis in light water produces the same amount of energy as that of palladium in heavy water. Besides, we have to consider a no less mysterious phenomenon of sonoluminescence that was discovered in Russia in 1933 by Professor Sergei Zhevkin. At first sight, these phenomena seem to bear no correlation. But Julian Schwinger, the Nobel laureate and profound research worker, has drawn parallels between cold fusion and sonoluminescence in his continuous technical publication on both topics. He notes in cold fusion. Like cold fusion, sonoluminescence should not exist, but it does. This now well-established phenomenon occurs when ultrasonic sound being into liquid causes bubbles to oscillate stably, to expand and contract regularly, and also to emit regular pulses of light. But one is positively struck by the heat generator built Potapov, Kishinev, Moldavia, which produces in water cavitation bubbles generated 12 kilowatts and heat on 4 kilowatts of electric energy. This is achieved by the aid of a centrifugal pump that runs light water through a tube with a number of special attachments. Similar, though less effective results have been obtained in the USA by James Griggs. The reactions taking place in the above mentioned cases can be explained neither in chemical nor in nuclear terms. Moreover, Potapov's system is now in production and used for heating house. There is no doubt that the described phenomena can be viewed as new physics, and it is impossible to describe them within the limits of conventional science. Below, it will be shown that unitary quantum theory allows one to explain all the seemingly unrelated effects. Unitary quantum theory was developed early, and its validity is proved by the fact that at a limited number of cases, the theory results in both the Dirac's equations and the relativistic equation of Hamilton-Jacobi. Moreover, the solution of approximative unitary quantum theory equation has yielded the electric charge value and that of the fine structure constant with reasonable exactness. result being achieved for the first time in theoretical physics. The solution allowed to formulate one more approximate equation for the oscillation charge particles model, which gives promising results in dealing with the Pons interaction problem, the basic cold nuclear fusion problem. Let us consider more closely, as was done in my paper, the particles behavior in a potential way. Well, the equation describing that process can be expressed in following way. Where Ux is potential and x point t phi 0 a coordinate velocity time and initial phase corresponding. This equation manifests a number of peculiarities. Having integrated once, we arrive to equation 2, where W, where xt is some time-dependent complex potential not amenable for analytical expression even for the simplest x. Therefore, nothing can be said about the integrals of motion. Equation 1 behaves very peculiarly in translation, invariance condition. It doesn't exist in common case, but manifests itself or at translation divisible by p. That means that two classes of solutions are available. For the first class, the loss of energy and momentum conservation are valid, while for the second class, they are not. Numerical computation for the parabolic wheel solution of 4 types that results from different initial conditions. Similar results can also be obtained for other potentials. Solution 1. The stable standard periodic solution are obtained only for definite discrete energy E, well is equal to Z. Tried solution of the same kind are available in conventional quantum mechanics and will not be analyzed in this paper. And other initial conditions, 3 more types of solution arise. Solution 2. The particle performs complex oscillation of a diminishing amplitude. Sometimes of certain x point phi 0 values, the process starts and at an increasing amplitude with its consequent decrease. At this point, the particle charge and mass approach 0, and after some rather long period of time, the former ceases to exist altogether. This is not surprising because in unitary quantum theory, the particle is defined as a periodically emerging and disappearing wave packet. Its complete disappearance means that packets' harmonic constituents have scattered so far from each other that the packet still ceases to exist, its energy given away to the vacuum, smeared or thrown out to empty space, manifesting itself only in the form of vacuum fluctuation. Let us call this solution a crematorium. Solution 3. The particle performs complex oscillation with an increasing amplitude, yet sometimes the process can develop with an initial short time decrease in the amplitude. In doing so, the particle's energy can increase indefinitely if the potential wave parameters do not change. Physically, that means that the particle takes energy from vacuum fluctuation, but the mechanism of this process, of how it does so, can be deduced only from equation 1. Let us call this solution a maternity home. Solution 4. There is also a diffusion solution in which the particles tunnel into potential gap well. This solution is similar to that of the particle's behavior at the potential state when the particle in the course of considerable period of time can penetrate deep into the step. Periodic and irregular oscillations determine the energy discrete and continuous region respectively. From a purely aesthetic point of view, it is desirable that the quantity of energy matter disappearing in the crematory should be equal to the emerging from the maternity homes. But I am not yet in position either to prove or disprove it. Solution number 2 and number 3 are incompatible with conventional quantum mechanics, when solution number 4 corresponds to exponentially decaying damping out wave function tail at large x values. If the system contains a number of identical values, at all the decision of type 1 will be identical for them, and that's the reason for why the discrete energy levels are easily traced out in the experiment. But there will be no discrete levels for solution of time 2 and 3, or maternity home or crematoriums, because each individual decision will possess its own peculiarities. The availability of this solution can be perceived only through integral effects, either the energy realized or drastic charge or mass variation in the system, being in itself a very specific phenomenon. Let's take a more close look at intriguing solution, crematorium and maternity home. I was aware of them as far as 5 years ago, which can be, but I was afraid to discuss the matter in my publication in the absence of reliable experimental data. Even now, I am in mortal fear lest my reasoning turns out to be erroneous. But the situation has since changed, and one can say now with certainty that within unitary quantum theory, in quantum processes, the energy and momentum conservation law have grown from local to a global one. Anderson, in individual processes, the energy and momentum are not conserved, but might be taken or given away to the vacuum. Nevertheless, there exists some range of phases when the energy and momentum are preserved locally. Being summed up throughout all phases for a large number of particles, the resulting energy and momentum terms ought to be conserved as is shown by calculation in my paper. The experiments show that in individual quantum processes at high energy, the local energy and momentum conservation laws and conservation laws for the lepton and baryon numbers are well observed. But the same is not true at small energy, at least on account of ambiguity correlation. Nevertheless, the idea of global, not only local energy conservation law, is invisible, present in all quantum mechanics. It is by no means and no new one. From a physical viewpoint, it simply means that in steady state solution is fixed discrete energy. The velocity of particles reflected at the well is equal to that of the impinging one. If the particle speed decreases upon each reflection, this corresponds to the crematorium solution. In case it increases, we face the maternity home alternative. The crematorium solution should not be confused with the familiar phenomenon of particle decay. It is an absolutely new and very slow process taking place at small energy. It possesses no analogs in conventional quantum physics. The maternity home solution has been proved by reliable experimental data for any small cavity in a metal or ceramics made sample, or likewise a water bubble with enclosed free particles and can be viewed as a well. This can explain both sonoluminescence and the emission of heat in nickel, palladium, and ceramics. The theory allows for the samples to crack because of the pressure accepted on their wells due to energy growth, the energy generation being immense in the installation by Potapov and Greeks. Thus, the excessive energy is taken from the vacuum, but it does not occur for nothing because in the neighboring wells some part of the matter will disappear. In other words, one is under the impression that a new mechanism for the direct conversion of matter into energy has been discovered. This energetic phenomenon is entirely pollution-free and thousands times more effective than of nuclear reaction. It is for the future to prove it. Now let's take a bit of philosophy. The local energy conservation law in individual processes follows directly from Newton's equation under the condition of uniformity of time. It would be naive to think that his local definition will remain unchanged. The trend in modern physics now is to treat the local energy conservation law, especially in theory, as a conclusion on secondary importance from the motion equation, integrals of motion. Some physics confine local energy conservation law within the limits of the first law of thermodynamics, others as Dmitry Blokhintsov maintains that it is highly probable that the development of new theory will make local energy conservation law change its form. The idea to treat the energy conservation law in quantum mechanics equally with the second law of thermodynamics as a static law, being true only in average cases insuitable to individual acts, goes back to Schrödinger and later Niels Bohr, Kramer, Slater, and Georgi Gamow. Lev Landau had called it a beautiful Bohr's idea. Yet later it was rejected by the authors themselves. It should be noted that this idea did not follow from the quantum theory equation, but the brilliant idea still remains one, even being rejected by the persons to whom it had appeared. In fact, it may simply turn out quite premature. Eventually, all the cosmologists dream of having a process explaining why throughout the entire universe there are some places where energy emerges being extinguished in the others. It is interesting the solution maternity homes gives one an opportunity to set a very small initial fluctuation which then will accumulate energy and turn into a particle. One has to accept a true regards of this sort. Therefore, I will conclude with the words of Friedrich Engels. But when the solar system completes its life path and shares the fate of everything finite, when it falls victim to death, what then? Thus we come to the conclusion that the heat emitted into all space should have an opportunity by some miraculous way, which it will be the task of future science to define, to turn into some other form of motion in which it can accumulate again and start functioning. In this case, the main difficulty becomes obsolete, the one obstructing the reverse change of their suns into a red-hot nebula. One can expect that having read this report, some highbrow theoreticians will assume attitude of persons being witness to some childish tactlessness. But in the course of physics development, it was experimentation that would have always been the main judge. I did like to express my gratitude to Fred Jagger, Dr. Finadeev, Dr. Boychenko, Kazakov, Rudoy, Kulikov, and mine. Thank you very much for your attention.
What did you calculate? You said you calculated the mass spectrum for electron, mu, neutrino. What did you find for the mass of the three neutrinos?
Так, значит, я получил выраженный спектр масс. Значит, из массы нейтрино одна масса, две массы нейтрино, порядка, я сейчас вспоминаю, 5 нейтронных масс и 20 нейтронных масс. Нейтрино.
То есть вы получили массу.
Нейтрино, это электрон, это точно протон.
It was obtained mass of electron,
Протон,
proton,
значит, ромезон, мюон,
romizon,
мюон,
muon.
мюон,
No, ma poi
мюон.
devo sapere il masso della...
Так, с точностью порядка 1%.
And accuracy was about 1%.
No, it gave a mass of neutrino there. It said neutrino. What was that mass of neutrino?
Масса нейтрино несколько электронов. 3 нейтрино. У меня вырожденный спектр.
Oh, this is degenerated mass spectrum.
2 нейтрино.
This is
No, there's 3.
Degeneration spectrum. Degeneration.
degeneration spectrum, mass spectrum.
Thank you.
Così.
Was another question? Some other questions?
I understand.
Some other questions?
Okay, if not, thank you again.
Да, я не забыл, я не
Now there is for interaction palladium hydrogen isotopes confusion by
So 1.5 years ago, I gave a presentation in Hawaii. The title was Cold Fusion by Sparking Hydrogen Isotope. You can see that the title is slightly different. It's Interaction Palladium Hydrogen Isotope and smaller, lower, Cold Fusion by Sparking Hydrogen Isotope between brackets. This is the first comment on the title, and the second comment I want to make first is that I'm using a discharge in a high pressure gas, which is completely different from a glow discharge, and we could discuss that at length 2 years ago in Hawaii. So I will give you the result of the search for nuclear ashes and radiation from fusion reaction in the system either hydrogen palladium or deuterium palladium. I will give you some results on the excess energy of the system pure palladium, pure hydrogen, and I will point out to a number of problems which occurs from these results and some indication on how to explain them, and I will give a conclusion on all that. For searching nuclear ashes and radiation, we used the reactor which has been described already 2 years ago, so I don't want to go in detail. The typical excess power which was yielded by this reactor was and still is 2 watts. We have looked for the 3 ashes which could be expected from the classical D plus D reaction, which are helium-4, helium-3, and tritium. And we have looked also for neutrons and for X and gamma photons. I am not going to enter into details in the techniques we have used because we can discuss that at length around the posters if people are interested. Just say that helium was measured by high resolution mass spectrometer with sufficient getters to get rid of deuterium, etc. So the sensibility is very high. In the gas phase, in the electrode, by fusion of the electrode in a furnace inside the mass spectrometry. It's a very nice device, which is not in our laboratory, which is in Bordeaux, in Centre National CNBG in Bordeaux. and they have a great expertise in looking for helium in meteorites, for instance. Helium-free tritium was determined by combustion to water in scintigraphy. The conclusion, I will show you one or two special slides on that. The first conclusion is that helium-4 and 3, which was found in the gas phase, were obviously coming from a leakage because we followed also the neon. So we could make a number of calculations clearly showing that within the experimental errors, it was leaking from the outside. Second thing which can be said is that we have found very small amounts of helium-4 and helium-3 in the electrode, which we cannot explain by obvious artifact. I'm not saying that they have been generated by cold fusion. What I'm saying is that we cannot explain them by obvious artifact. The obvious artifact in the system we use, of course, is ionic implantation, because if you have helium and neon in the gas phase, you can implant them in the electrode. And we have used a method which I'm not going to enter in to discriminate by considering the ratio helium-neon in the electrode and taking into account the difference of susceptibility to temperature of the diffusion coefficient of these two gases. If it is ionic implantation, the points here would be around 1 or below 1. So you can see that a number of helium production is only due to ionic implantation. The only doubt we have is on these points. These two are nitrogen, by the way. This is deuterium. And these points we cannot explain by obvious artifact. Anyhow, the quantities are very low, are extremely low, because the upper limit of what might be helium production is lower than 10 to the power 5 per second, which is very low compared to 2 watt, and for helium-3, lower than 5 to 10 to the power 3. And we didn't see any tritium, but we didn't use a very sensitive method. So within the detection limit that is less than 2 to the 10 to the power 3 per second, we didn't see any tritium. We have also looked for radiation. We have looked for neutron with helium-3 detectors, and we did some, of course, energy spectrometry. We looked for gamma and X by either ionization chamber and solid scintillation counters, also with energy spectrometry. The conclusion is very clear that the neutron we measured were background. We had some burst which was caused by a number of electrical pickups which we could identify. The photon by ionization chamber was also background. We have some observation of low energy spectrum under certain circumstances, but for the time being we don't say anything because we have not yet studied that in detail, and we cannot say if this is only artifacts or it is something real. Just to give you an example, this is neutron recording on 3 months. Well, you can see that with 2 detectors, one has a wider window than the other, and you can see that typically this is the number of count multiplied by 10 to the power 3 per second, so it is typical background value. This is the indication of the increase of power of one experiment. You can see that, of course, here you can say the background is that you have 5 times more than the background, and you are correlated with the increase. But if you look the whole thing, you can see that the background is fluctuating with some fluctuation. Here you have, of course, the introduction of a neutron source, which means that the counter sees the neutrons. And I eliminated from that some burst which were due, in fact, to electrical pickup. So there were no neutron detected. So I will insist on so the question we asked us was, we have an excess energy with deuterium, we have checked that. We do not see nuclear ashes at a level which might explain this excess energy. So let's see, with the most simple system, what happens about excess energy. So we choose the system pure hydrogen and pure palladium. We changed our calorimeter, that is, we built a new one. So I will describe briefly the material used, the reactor used, the type of calorimeter and calibration we used, the hydrogen consumption measurement, the palladium loading ratio, and the results. This is the material we use, very pure hydrogen, very pure palladium. I go on because all that is on the posters if you want to discuss it. Reactor used were ozonizer type reactors, which I can also discuss at length with people interested. Just one important point, we use two types of reactor, one with one dielectrical barrier. In an ozonizer type of reactor, you have between the electrodes, you have a dielectrical barrier. So you can have one dielectrical barrier or two dielectrical barrier, and this configuration is very interesting because you can do very representative blanks, because you can struck a discharge in hydrogen with no metal in contact. So you are exactly in the conditions where only hydrogen is activated with no metal in contact. So I will go over the schemes of the reactor just to show you how it looks like. It is a tube. You have two palladium wire, you can see on blue here, and you have an outer electrode here, and in between a tube of Pyrex, which is the dielectric barrier. Those who have looked at ozone production know how that works. We have changed completely the calorimetric system that we have used for the Hawaii presentation. One single calorimeter contains the reactor and the high voltage generation system, so there is only one calorimeter. The major part of the heat is recovered in a flow of oil, something like 95 to 99%, and the rest is exchanged with the air and is determined by calibration, that is, yields a linear relation between the heat loss and the difference of temperature between the calorimeter and the lab. And the electrical power is measured, it is an alternative field, 5,000 Hertz, but it is measured with a high precision numerical wattmeter with a high sampling frequency. Just to give you an impression, this is the calorimetric system, which we can discuss, of course, at length for those who are interested later. So we have run a number of calibration on different ways. We have used resistors with cosinus phase. We can change the cosinus phase very easily. Cosinus phase varying from 1 to 0.35 because the discharge introduced a cosinus phase in the consumption. We have used discharge in argon, and we have used discharge in hydrogen with double dielectric barrier, which means that you have exactly the discharge you are using in active experiments, but with no metal in contact. First conclusion, all calibration runs are on the same correlation, and the typical standard deviation, a run is, in the mean average time of run is 1 month, with runs varying from 3 weeks to 1.5 months. For one single experiment, the standard deviation is 0.3 watts, and for 4 runs, including 3 dismantling of the system, the standard deviation is 0.7 watt. So this gives you an idea of the stability of the system, and I will show you the calibration. Very quickly, to determine the calibration curves, we do this calculation: energy lost to air equal energy recovered in oil minus electrical energy in, which we correlate with the difference of the calorimeter temperature and the lab temperature, which yields a K coefficient. And for the active runs, we have excess energy, of course, equal energy in oil plus K time T cal minus T lab minus the electrical energy in. When you plot typical calibration yields this figure, if you look at the upper graph, I've plotted here the difference between the calorimeter temperature and the lab temperature, and here the losses calculated as I told you. And you can see that you have a nice linear relation between these two quantities, and you can see that these points are discharge in argon, discharge in hydrogen with double dielectric barrier, and discharge with resistors are all on the same calibration. I will comment these points, of course, later on. Before giving you the results of the excess heat measurement, I want to show you how we measure the consumption of hydrogen. It is a very simple system. We have a reactor, which is of course in the calorimeter, and we start the experiment with a reservoir of 300 cubic centimeter at 5 bars, initial pressure of hydrogen, and we have a regulating valve here which maintains the pressure of the reactor. We record the pressure here, the pressure and the temperatures, etc., so we can very easily measure the quantity of hydrogen input the system. Knowing the amount, of course, of palladium which is in the reactor, we can calculate the loading ratio rather easily, or at least the apparent loading ratio, because you will see that you have some curious thing happening. And of course, we followed also the loading ratio by measuring the resistivity of the palladium, which can only be done when wires are used. When we are using foils, which is the case, we cannot measure the resistivity. And this is only a relative measurement because I do not know the temperature of the wire. Okay? So if I would like to summarize the results on hydrogen and palladium, that we get no excess energy when the loading ratio is too low. That's not a surprise. I think everybody is agreeing on that. And the second result is that when the loading ratio is higher than 0.7, we have excess energy, which were up to 5 watts, increasing with time. We will see the results. And a very strange behavior of the apparent loading ratio, which is not explainable, of course, by leakage of hydrogen, which was the first thing which was checked. So first, let me see what can be stated as another blank experiment. This is an experiment which didn't yield any excess energy. We know why, and because the palladium used was not of good quality, and we found it with scales afterwards, after the experiment, meaning that no high loading ratio could be achieved. So if you look at the apparent loading ratio in that case is perfectly normal. You get an increase at the beginning of the experiment, and then something like 0.7, 0.75, which remains for 20 days. And if you look at the excess energy, you can see that the excess energy is typically in the noise of the system. It is typically 0. So bad quality palladium in our system yields 0 excess energy on a period of 20 days. This is 2 million seconds. And the pressure of the system, or the consumption, or the loading ratio is constant. Okay? Now I come to an experiment yielding results. The behavior is completely different. You are starting to get out of the noise somewhere here, and the thing is increasing. This is perfectly explainable. It's just by changing the operating conditions, but I have to hurry up because it's only 5 minutes left. And the apparent loading ratio is extremely surprisingly going to 5, which is completely aberrant. So that is why I put apparent loading ratio. Very briefly, these points are very significative of the excess energy I showed you, and you can see that they are completely out of the base of the reference correlation. So you can make a number of... The thing which is very interesting to plot is to plot the cumulated excess energy as a function of the cumulated hydrogen consumption, which is measured by the pressure balance of the system. And you can see that you have 2 at least two straight lines which can be drawn, one in this period and one in this period, which I did here. And this corresponds to 6,000 EV per atom hydrogen, and this to 1,500 EV per atom hydrogen. So it's very interesting because you have a measure of the number of the energy per atom hydrogen. I'm not going to comment on a number of things which we checked, of course, about the loss of hydrogen which could happen in the system. We checked that there was no leakage, there is no leakage of the system. You saw an experiment which was perfectly normal. There is no combination with any element in the reactor because there are very few elements in the reactor apart from palladium. So the conclusion is that a reaction occurs with high energy per atom hydrogen, up to 6,000, and hydrogen is lost in an unexplainable way with no leakage, no combination with material in the reactor except palladium. So we have to find something to explain that. And for the time being, our explanation is that a bound state between hydrogen and an electron occurs. I don't want to go into details because my time is running. I'm running out of time. That we think, the hypothesis we have for the time being is that in the conditions of the experiment, we form a bond state between a proton and an electron, which probably occurs at the occasion of a jump of a proton from one octahedral side to another, and that this thing is very small, some 300 femtometers, so it can diffuse out from the reactor. And the second thing which this thing might do is, of course, to be confined close to a nucleus, because it is polar, and then you can imagine a number of reaction of the type of enhanced electron capture, which can work very well with lanthanum, for instance, with potassium, which are already natural electron capture elements. If you add an electron close to the nucleus, you can increase this reaction. You can dream of double electron captures. These are possible with palladium, nickel, iron. By possible I mean they are exothermal. Most of them are not exothermal, but all these reactions are exothermal. So you can find lanthanum, potassium, nickel, iron, palladium. Well, for the time being, this is only, of course, an hypothesis, but the experimental fact is hard, I think, and strong. So my conclusion would be, forget the Promethean dream and concentrate on a reaction which can yield up to 6,000 EV per atom. And the figures which are here, if you multiply 6,000 by 500, you get the typical excess energy from the DD reaction. And if you divide by 6,000, you get the typical excess energy yield by combustion. Thank you for it.
Very similar. You remember, we find the hydrogen gas pressure was dropping, but then we went at the nickel, there was no hydrogen there. Maybe this is very happening. Nickel hydrogen.
Regarding your hydrogen loss, what kind of tubing did you use to transfer your hydrogen?
Essentially, stainless steel tubing, and the reactor is from Pyrex. Okay.
Thank you very much, Dr. Dufour. Next, we move on to a presentation by Dr. Srinivas of the Barber Atomic Research Centre, and the title of his talk is... he just changed the title of his talk,
well,
which you were now saying.
I think that was...
I have the thing.
Oh, thank you.
Sorry.
The title given in the abstract booklet is kind of ambitious, and at this late time in the day when all of you are as tired as I am. I don't think I should go through such a complicated review. But what I would like to mention is, perhaps some of you might remember, we had presented some interesting results in the first Salt Lake City meeting on observation of tritium on a titanium anode loaded with deuterium. And but however, since then we couldn't really repeat it, and in our own laboratory there was sort of a decrease in interest in the use of a plasma focus. But during the last few years, there have been a number of new developments. For example, people have observed that application of an RF field helps cold fusion phenomena. This is Lex and Bockris and others. People have noticed magnetic fields. The Piantelli experiment, for example. I don't remember the author, but microwaves have been used to improve the phenomenon. Ion beams, of course, Stringham, Kasagi, Takahashi. Plasma loading, perhaps we can say that the use of a plasma focus was perhaps the first occasion when plasma loading gave results. Since then, as you know, my previous speaker is also using plasmas, so that has come back in vogue. High currents passed through the sample seem to somehow stimulate. Importance of clean surface has been mentioned by many people. When you subject a plasma, an anode material to a plasma blast, it gets thoroughly cleaned. Microsecond pulsing has been mentioned by Hilani, therefore very short pulses might help. So these things seem to suggest that if there's a device that can produce all of these, maybe some interesting phenomenon can occur. So the plasma focus essentially is such a device. I now go on to a very brief description of what it's all about. Many of you are not familiar with the operation of a plasma focus. The plasma focus belongs to the family of dynamic Z pinches. It forms a high density and high temperature plasma. The pinch phenomenon, as you all know, was initiated in the early 50s. In a pinch phenomenon, essentially you have a gas through which you drive a very high current by discharging a capacitor or something. And this very high current, due to the J cross B forces, collapses and implodes. The plasma sheet collapses on itself, forms a pinch. Pinch eventually disrupts due to sausage instability. This is the good old Z pinch. Now, what people in the early 60s found, if I remember correctly, it was more or less simultaneously discovered both at the Kurchatov Institute and Los Alamos, that this very interesting geometry gives rise to this concept of a plasma focus. So let us now look at this little figure. We have here two electrodes. Essentially these form a coaxial gun, and the anode and the cathode are separated by a Pyrex glass insulator, an alumina insulator for example. It's a very thin sheet. The two are connected, evacuated and filled with hydrogen gas at a very low pressure, and it is driven by a capacitor bank charged to maybe 20, 30, 40 kilovolts, and when the spark gap is fired, this high current for a very short time passes through along the surface. A surface discharge is formed, and at this point there is a J cross B force, a very high magnetic field which unpinches, or what is it, removes the plasma from here, and a sheet forms between the anode and the cathode. This sheet is driven down like a linear accelerator or a coaxial gun, and at the end of it, which is open, at the open end, the sheet collapses on itself to form a plasma. The whole thing occurs within a microsecond. It was accidentally discovered, as I said, in 1960 by Mather and Los Alamos, Filippo. The Filippo geometry is a sort of a horizontal flat geometry, and this is a tall geometry. Now, the beauty about the experiment itself is very simple. But the plasma that is formed, here is a slightly better picture. This is the anode, this is the cathode, the whole thing is in a vacuum chamber, and the focus forms here. There are three regimes for the focus. People have studied this for the past 25, 30 years. At least several hundred PhD theses must have been taken out on a plasma focus device. The three regimes are the rundown phase, the compression phase, and the post-focus phase. And as I said, each phase has been studied separately by different groups, and very, very interesting things occur in that. Just a little bit to tell you about the rundown phase, which in turn consists of two phases. First, what causes the breakdown, and then the acceleration phase. The acceleration itself takes the few, maybe 1 or 2 microseconds by the time the focus forms. The actual focus lasts for less than a few hundred nanoseconds. Now let me see what we have. I can say a few things about the compression phase. The During this phase, the current sheet is driven along this. Particles escape both on both sides of the axial, the pinch both in the top and bottom. Part of the magnetic energy, first you start from the stored electrical energy, which is converted into magnetic energy behind the sheet, which in turn is converted into particle kinetic energy. And during this period, ions are preferentially heated during the implosion phase, and very high energies are produced. Although we apply only 40 kV or 20 kV to the device, ions with several hundred kV have been found due to mechanisms inside the plasma. The density at the focus is about 10 to the 19 electrons per centimeter cube, and the collapse speed is about 10 to the 7 centimeters per second, and so on. These are the properties of the formation of the focus. In the post-focus, now this is a pictorial view of how the whole thing occurs. This is the pseudo-cylindrical implosion, and by the time it fully pinches up, this thing m equal to 0, sausage instabilities occur, and the whole pinch disrupts. And during this time, somewhere down the time, lots of neutrons and all kinds of X-rays and gamma rays, all kinds of things are produced, which has been studied over the years. This is an Imicon picture of the series. As I said, students have fun observing these things, making all kinds of measurements. I think I'd better go on to the slides which I've had. If somebody can help me switch on the slides. I don't know where there is this remote device. This is a picture of one of our earliest capacitor bands. There are 6 capacitors which are connected together, and there is a collector plate. The only electrical requirement here is to keep the overall inductance as low as possible, so that the entire energy, stored energy, can be discharged in a couple of microseconds. And so this collector plate helps to do that. Very low inductance device. In this particular case, we have what is known as squirrel cage type plasma focus, and there is scintillating photomultiplier tube for making measurements. Next. This is a more recent version of these used capacitors manufactured by a firm in Milan. This is the collector plate. This is the plasma focus. This is various measuring devices. It is filled with hydrogen of a few millibars, hydrogen or deuterium. Next, please. This is a closer view with various experimental units here. I will not get into the details. Next, please. Another closer view of the plasma focus itself. Next. This is a single capacitor. Just with one capacitor, we can do equally good experiments. This stores about 2 kilojoules of energy. The previous one was about 10 or 20 kilojoules with about 5 capacitors. Next. This is the spark gap on top there. This is a single capacitor band, spark gap inside there, plasma focus there, and he is making some measurements for neutrons. This is probably a silver activation counter to measure the total neutron field in the experiment. This is a vacuum system and so on. Next. Closer view of the same thing, measuring the pressure here. Next. This is the squirrel cage plasma focus. Right there in the center is the anode, and these copper rods are the cathodes, and the whole thing is mounted on connected. This is the central anode which is connected to the capacitor, and the current goes through that and comes out and forms the sheet. Next. Now this is an X-ray pinhole shot of a plasma. This is a plasma focus proper. You can see the m equals 0 instability, the plasma is trying to disrupt. Somewhere here is the anode. Now it is this that is of interest for us. The purpose of the whole thing is to produce such a plasma. It is a hot plasma, several kV in temperature, but all kinds of things are happening, very interesting things. It produces, as I said, X-rays, neutrons and so on, circulating ions, which if you keep a material here, which is the central anode, and if you make the central anode either of titanium or palladium or something, it does get loaded. The only point to be noted here is in a normal operation of the plasma focus, where the central electrode is functioning as an anode, the ion beams are preferentially, the deuterons or hydrogen protons are preferentially accelerated in upward direction, whereas the electrons are accelerated downward and they bombard the target, producing X-rays. So if you want to load the target, either you should keep the palladium there or reverse the voltage of operation. Next, please. Next. Well, this is another shot of it. Somewhere there are some hot spots, not properly focused perhaps, but anyway we'll keep going through. One more of these, very nice little picture. This is a top view of the plasma focus during the implosion, and you can see it's about 5 millimeters in diameter and it's about 2 or 2.5 centimeters long. Next. These are now, the plasma focus has some very interesting properties. If you take this pinhole shot, you do find some hotspots. So just as in palladium, all the terms anomalous reactivity has been used for the past 20 years in connection with the plasma focus. The neutron production mechanism even today has not been fully understood. Anomalous high reactivity of the system. It is now known it is not due to thermonuclear mechanism. It is mainly due to deuterons which are accelerated to very high energies. The same deuteron acts as the target, so we have beam target mechanisms. Now there are phenomena by which these hotspots are produced. There are two groups, Bostic and Nardi, somewhere in Stevens Institute, who produced very beautiful pictures of phenomena which occur there, but I will not go into it today. Next, please. Some of these hotspots, hard X-ray. These emit X-rays of almost 200 T. Next. Now I come to the central anode. This was the first, this is the titanium anode. This is a picture from which I had shown in the Salt Lake City meeting, and this is the titanium anode which gave us about 400 microcuries of tritium. It's a fantastic amount. You can see this completely eroded here, and let me go to the next one. Next one, please. Another view of the same anode. Even today we have it here. Next. Now this was a fascinating picture which was taken in February 1990, which was shown at the first meeting, and this is an X-ray autoradiograph. Let me see what this number of hours of exposure. If I have it here, probably I don't. It was probably an overnight exposure of 24 hours, and the same anode was stuck in front of an ion chamber and gave us plenty of current, and we saw the beta spectrum, all kinds of things. Now what we did learn from here is wherever you see all around the edge, where the titanium was machined, where it was cold work, where the lattice is probably damaged, there seems to be plenty of absorption. And it's telling us something, but we haven't understood precisely what exactly it's telling us and how to interpret this. This is the titanium anode. Next, please. This is deuterated. Now this was taken 2 months later. This is April 1990, 2 months later, almost the same pattern. We were hoping we could use an image comparison mechanism to find out whether there has been a change in the pattern, but we haven't succeeded in that. Now I'm going to show you the same thing taken last month. Next, please. 5 years later, it still has the same shape, the same amount, same shape. This is again something fascinating. The diffusion of deuterium or tritium in titanium is so slow. Pattern remains for 5 years, and even today we are able to get the same thing. Now this is again with an X-ray. This is probably a 65-hour exposure. Next. This is about, I showed this on the first day. This is taken with this new image plate technique. It's also showing the same pattern. So this is from TLD kind of material. So this is the kind of, let me see, do I have something more? Next. These are hydrogen. When we found fascinating pictures with titanium, we decided to try palladium. Now there's a little bit of interesting history, and of course when my colleague loaded palladium, every palladium deuterated sample gave us this beautiful autoradiograph. But then we couldn't see any betas on the beta counter, so he loaded with hydrogen, and to his surprise, he found even hydrogen was giving. This was 5 years ago. This is how we stumbled upon the phenomenon of palladium hydride luminescence. Since then, we have been trying to understand. I mentioned about this in the first day. Next. Now, I think I should tell you what this was. Now, that was a palladium piece. 15 shots were taken, 65 hours of exposure. There was a gap of 1.5 millimeter between the palladium transect and the X-ray film. And in that particular case, a voltage of plus 100 volts was applied during the autoradiography. The idea was to try and find out whether the autoradiographic image is occurring due to electrons or there is some positively charged particles coming out. So we did autoradiograph both positively applied voltages during the autoradiography as well as negative. And both of them gave us same kind of pattern, so we don't know, we couldn't conclude what it was. So this is the second one with 13.5 volts voltage applied. Next, it's a different shot, a different day. This is with minus 100 volts. I couldn't come to any conclusion about the nature of the particle coming out. This is all in air, this is not in vacuum. Next, this is with 500 volts, minus 500 volts, and still they get the same kind of pattern. So this is all palladium hydride, no deuterium in this. Next, well, having come to this, we have funding through the hot fusion program to build a bigger bank. So for what it's worth, I'll just show you, these are one rack of 8 capacitors. This will give us 50 kilojoules. We have 3 such racks, so we are in the process of building a 150 kilojoule bank. But next, just to show you the technical thing involved, to keep the inductance down from each capacitor, we have to have 4 such cables. So it's more of an electrical engineering work involved in this. Okay, I think we'll skip the slides. I'll go through, just given me the signal. Just to give you an idea of what is happening with field, the title was originally given as past, present, and future, so I should tell you. Plasma focus research is conducted in about 50 laboratories in the world, and of these, there are at least 15 labs which had 150 kilojoule banks. I'm told that many of these groups have sort of lost their funding to carry on. For example, the Frascati 192 bank, I think, is shut down. Studies have concentrated on studying the properties of the plasma focus primarily, like in cold fusion with a lot of variation, short-to-short variation. People have understood the effects of gas pressure and the impurities, etc. have been studied. The influence of anode material on plasma, my colleague has just written a PhD thesis on that. He studied a number of anode materials. Now, in cold fusion, what we would like to know is how such a transient, rich plasma affects the exposed samples. Unlike all the previous studies where we have been trying to understand what is the role of the anode material on the plasma, we are now interested in asking how is the plasma going to affect the loading in that material. Now, I can just show you out of the various properties. This is a very early study of Earth. You can see here the point, the Trompe point. Now this is the variation of neutron yield versus the energy of the stored energy of the capacitor bank. This scale roughly has reached about 1.73, but the interesting thing is that we probably have the record of measuring neutrons with probably the lowest energy. I haven't come across any paper with this 100 joules is just a little bit of capacitor, and this is primarily because we had a technique to measure the neutron yield just 10 to the 5 neutrons. Now in the bottom, or maybe the next one, the same neutron yield is plotted as a function of the pinch current. Here again you can see the points way down here. This is just a 100 joule capacitor bank. We are now building somewhere here 150 kilojoules, 150 kilojoules, which might give us 10 to 11, 10 to 12. Now in the early days, there was tremendous interest in the I to the power of 4 scaling. So people said if only we could build a bank of about 10 or 20 megajoules, hopefully we'll get 10 to the 16, 10 to the 17 or so many neutrons, which could then be converted into a reactor. It was this that was fueling plasma focused research for many, many years. But unfortunately, when they did build the bigger banks, the neutron yields did not really come out as predicted. Not because the phenomenon doesn't work, but there is purely a technical question of the current being diverted through very rather leakage path. It just didn't go into the pinch. So all I can say is there has been a decrease in interest in the plasma focus throughout the world, particularly because of the recent revival of Z pinches using pulse power technology of 1,000,000 volts. Using Bloom lines is completely different technology which has come out of the defense research. They're able to drive Z pinches once again. So I have a feeling Z pinches driven by 1,000,000 volt bank, March bank, seem to be giving more promising results in the plasma focus. But our interest is not in the hot fusion properties of the plasma focus. We are more interested in finding out whether the plasma focus itself can be used as a method of loading various samples and try to see whether we can teach us something. Now maybe I should wind here or just one slide on the mechanism of neutron production, and then I'll go to the conclusion. Most of the neutrons are produced after the initial pinch disruption, Their spectrum suggests that they are produced by accelerated deuterons, tens to hundreds of keV in energy. Most deuterons are emitted from the area around the pinch, and a certain amount of flux anisotropy, etc. But the important point is the pinch does produce very fast neutrons which are captured in the plasma, which can bombard our samples and probably give us very high loading. So with this, let me just come to the concluding slides. I have probably two here. The plasma focus apparatus is a very simple tabletop machine by means of which we can expose various metallic samples to a very, very rich, complex hydrogenous plasma or deuterium containing plasma. Indeed, it's a micro explosion that is created above the sample, which consists of deuterons of hundreds of keV, electrons of hundreds of keV, very high magnetic fields approaching a megavolt for very high currents, and the current runs to the hundreds of kiloamps. The magnetic field around the center of the pinch current is hundreds of kilovolts. Therefore, your sample being bathed in a high magnetic field, bathed by neutrons, bathed by electrons, and X-rays, and microwaves, and RF fields, all kinds of things. So one can certainly expect very interesting observations. Plasma discharge cleaning is not anything else, just cleaning the surface of the anode and exposing it to plain neutral hydrogen gas and helium gas will itself result in very good absorption. But in the presence of ion beams, you can expect very nice loading. It enables good absorption besides ion absorption. The only problem I see is that it is going to be very difficult to pinpoint what exactly has caused a given phenomenon in the metals which are exposed to such a mini plasma explosion. Because there are too many phenomena play a role simultaneously. It may however be but doing the experiment, anomalous pole fusion effects can be induced in a reproducible way. Thank you very much.
That's a big question on this very interesting paper.
Question and a comment. First of all, very nice talk. Great talk. Is there any indication of what a branching ratio might be for tritium and neutron production in these things?
Good question. In a normal hot fusion neutron yield production, people assume the branching ratio is unity. As far as I know, nobody has been able to measure the total tritium yield in such a thing very accurately. So everybody has been assuming it is unity, and I also would agree it's probably unity. Therefore, it will be important for us if we can expose some samples and find that in the samples the branching ratio is much higher. For example, thanks for the question. For example, in the particular experiment we did where the titanium anode produced 400 microcuries of tritium, the neutron yield was just 10 to the 6th. Whereas the number of atoms of tritium we produced on that anode, which is still there for anybody to measure, is 10 to the 14 atoms. So it is obvious that the tritium we have got in anode cannot be due to the hot fusion mechanism which occurs on the plasma film. Thank you very much.
I'm a comment. I think from my standpoint, this is probably going to be related to filament fusion, and Vijay's talk is going to bear on this too. But I think there's an interesting possibility for the electron catalyzed fusion model here, and that is this. When these pinches occur, you get a conductor boundary. This conductor boundary could affect the 0-point field magnitude next to it. This could cause electron collapse, which could induce the fusion. That's a possibility.
I think all kinds of things can happen.
Well, just one more quick question because we're very much behind time.
It's not really a question. We think in some way, in our system, we have very long wire and supply big amount of current density. We can add some way some localized fusion. Just my thinking. Do you have a comment about?
No, not immediately. I think unless we do the experiments and see. So far we have in the last couple of years we have not done any work to actually this thing. Now we are going to start. Particularly after I was really inspired after the Piantelli's experiment where he claims he's finding interesting effects when it is a lot of magnetic field is applied. So I would be interested in trying it out. Thank you.
Yes, in view of the time, I think I would propose that further discussion, which I'm sure will be plenty of, should be carried out around the poster. So now we move on to the last talk today, which is to be given by Professor VJ of the Laboratory of Physics Sierra Madre Curie in Paris, who has been collaborating with members of 2 institutes in Belgrade, and the title of this talk is Neutron Detection in Plasma Focus and Capillary Fusion Experiments. Thank you.
Okay, well, by profession I'm a physicist, not a sociologist. If I were a sociologist, I would very much wonder on the echo and the nature of this conference, because after all these conferences on cold fusion, the 2 essential points of the discovery of Pons and Fleischmann, namely the existence of excess heat, even in small quantities in certain types of experiments, and the presence of some fusion ash have been confirmed. We can discuss on the quantity of fusion ash and so on. But this sounds like a fantastic breakthrough in the field of physics, and as time goes on and more experiments support these 2 points, it seems the media echo is going down. So my opinion is that there are extra scientific elements in this discussion, and that new forces are really entering the discussion and new motivations, and therefore the scientific discussion is going to become more difficult, because the happy times of cold fusion are, in my opinion, gone. So how do you put that on? So there's quite a wide range of impressive experiments on excess heat and on cold fusion ashes, on fusion ashes. Of course, the situation is not so good at all in the theoretical domain. There's no widespread consensus on what causes the new phenomena. There's been very interesting contribution by Professor Preparata, by Professor Egerfeld, and so on. But we still don't know exactly what causes those phenomena. So I'm going to present the 3rd way of interpreting these phenomena, and which is much more conventional in a sense. But it's an old story in quantum mechanics. Bohr himself, when he discussed electromagnetic interaction between nuclei and electrons, had noticed that you should include magnetic forces, magnetic spins, in the calculation of the Bohr levels, but usually you just throw them away because the orientation of spins is random in the vacuum. So all right, now maybe the situation is different in the field of dense material, and my position I'm going to defend is that in dense material, the magnetic interactions become a very important force, because the Coulomb potential is 1 over R. The magnetic interactions are 1 over R3 forces. Therefore, you modify the Bohr levels, you find new quantum levels, and therefore you find new gamma rays and new X-ray emissions, and that the Coulomb barrier, everybody has assumed that the only way to go through the Coulomb barrier is to have high temperatures or kinetic energy, but maybe it is not so. Maybe there's a lowering due to the magnetic interactions, and then some screening by the electron clouds, which would facilitate some tunneling. So this is the model which I'm going to try and defend and present two experiments which have been performed with my friends in Belgrade. But as you will see, I'm very close to the explanation just suggested by Dufour's intervention and by what Srinivasan has just said on the importance of plasma focus. So, all right, let's discuss this a bit before I present the experiments. Well, all right. So maybe the way to go through the Coulomb barrier, you can find a way around it. Not by introducing new nuclear phenomena, but just by introducing the magnetic interactions in special circumstances. So you don't need to break the formalism of quantum mechanics. You just have to consider new boundary conditions, such as strong magnetic fields. So this is the argument which is defended here. So these are the assumptions which have been made. They've been presented already in Hawaii and in Nagoya. All right, now the problem is this changes. Every theory suggests experiments and suggests different ways of looking at things. So let's see what is suggested by such a model. So here you are. You can try to test directly the existence of new type molecular states. All right, so this I will show some of preliminary results. Some of them we obtained in Belgrade, but they just recover results obtained in the United States in Naval Research Lab. You can try to test mass spectroscopy. You could examine the decay of new type radioactive molecules. And there's an experimental cell which suggests things like that. And then you can try to detect those. Now this is a very important paper, by the way. It's in press in Physics today. I'll show some of their results, but it's going to be out in a few days. So as I told you, I just take for granted the excess energy and the existence of some nuclear fusion acids. So you can, an unpublished result is to study water plasma. So this means that excess energy appears because of the new type states due to magnetic interactions. So you can do plasma focused experiments, or you can do water plasma explosion devices in ceramic and metal cavities. And I will discuss briefly. It turns out that the assumption to use the nuclear spins in order to get energy is an old assumption. By the way, the paper is just posted there in the hall. It's a very important paper by Ramsey. There's 56, and the observation is essentially that if you have oriented nuclear spins in dense media, this behaves like a new phase. And therefore, you can use a Carnot cycle and eventually extract energy from that lattice. And in fact, Sam Ramsey himself did some experiments with lithium. All right, so this means that I'm not claiming any priority on that business. In fact, I discussed it just before he died with one of my friends. Some people may know him. He was called Azim Barout, unfortunately dead. So let me just show you a simple experiment. If you pass you make a discharge in lithium with heavy ammonia in a capillary, there's been these experiments were performed by Rusty Holgren. It was capillary fusion experiments. We just did a discharge in a plasma with lithium and heavy ammonia, and you have here the plot of current with respect to the time. And it turns out that in such a capillary, the current splits into beads exactly like they split exactly in this way. You can see the drawing here, the way the thing split. This is a picture taken by plasma focus explosion by Setyan in the Naval Research Lab. And of course it turns out that the neutrons which appear in that experiment, the thing went up to 10 to the 6 neutron per burst. The neutrons are just emitted there in that small region at the origin there, namely just when the beads are formed. And of course in such a model, the idea comes immediately that this is the result of the creation of the new pipe molecules or new Bohr levels, and that explains why this is an exothermic reaction. So I have no time to discuss the theory, but the theory is nothing mysterious. You just, well, I agree, I was criticizing one of the posters here, but I agree my calculations are rather primitive and with approximations. Namely, the real theory should be relativistic and so on, but I just used the usual non-relativistic Hamiltonian, which includes the Coulomb potential plus the spin magnetic interactions, and you have, of course, to go into the rest frame of the system and do the usual quantum law. So any student can do a calculation like that, and so finally you eventually find potentials like this, and you find new orbits. So now the problem is, if there are new orbits, how can you prove their existence? All right, so let's try and build a molecule like that. You can build a molecule like this, and you can try measurements. All right, so now let's go to the experimental part. I don't want to enlarge the theoretical part because there's nothing mysterious in that game. You better use a beta equation, but of course you better work start with the Schrödinger equation. So you're not doing anything special. So the only thing experiment in grade, I have friends there since the Second World War, is to make a good neutron detector. In fact, that was the only success after 2 years of hard work. We finally got, as you will see immediately, a good neutron detector. So we made X-ray neutron and X-ray, soft X-ray measurements. And as you will see, 2 results were obtained. First, you can stabilize, you
left to give details, but there's a poster outside which explains the way that the neutron detector works. It's nothing very special, and you have here figures which shows efficiency of the neutron detector. But there are two astonishing things which appear very clearly. I think they just confirm what Dufour has just said. Namely, you see regular explosion bursts of neutrons at a very high level. We started at 10 to the 8 burst, and we are now at 10 to the 10 without using any tritium. You can meditate on the consequences, and you find this is the neutron detector efficiency. This is a machine on which I'm probably, all right, let me go fast. So I'll show you just a machine. Here, I'll go over that. This is the bursts of flame. And the theory tells you that you should see a very narrow line around 10 keV and around 40 keV, and that's exactly this is the table for the data utilized. So these are my conclusions. And now let me show you the lines. Pretty good. There's nothing special in that equipment. In fact, the equipment was not very, very good. Here's lines which you obtain, very narrow lines, and they fit pretty well with the new ball orbits calculated with magnetic interaction. Okay, so I want to show something else. So this is just very strange phenomenon, because all the electric machines which we are utilizing, they all depend on magnetic fields and on the gradients or the variation of the amplitude of the magnetic field. And the square varies the square of the varies like the square. And so you can imagine very nice machine. There's an engineer who has proposed a very simple machine, namely, you have it you can imagine a machine like this. You have a stator there, right? And then you have the corresponding motor, something like what was discussed. I suppose you find a trick where you can densify the lines, build the tight ball orbits in the state, and you squeeze the Faraday bundle in the stator, well, then you would expect an increase of current. Well, some experiments done that are not confirmed that. And I heard that there were some Japanese society doing experiments along that line. Namely, if this interpretation of cold fusion is correct, I don't know, I mean, we don't have enough data yet. If it's correct, then it opens a whole new class of energy producing basic machines, but what you are constructing there, of course, you have a two-stage rocket. You start with magnetic interactions, then you can facilitate fusion, go around the trouble of the Coulomb barrier through tunneling